Yes, here we have some brief overview of what we'll cover with my presentation today. I will begin with the state of art of reuse in California, then I will delve into feasibility study of use of recycled water in Napa vineyards. Then I will talk about sustainable use of reclaimed water through new technologies. At the end of the presentation, I will show you some information about the state of art of a perspective of use in Chile. So here we have a map of California. Here are represented the 708 wastewater treatment facilities distributed in the entire country. They can be divided in 421 wastewater treatment plants, 267 wastewater treatment plants that produce recycled water, and 20 treatment plants that produce recycled water, but these treatment plants do not receive raw water, so treat already treated water, and in particular these are used for producing potable water. Here we have a distribution, some information about the influence, effluents, and the recycled water producer over 2019, 2020, 2021, and it's possible to see here that recycled water in California is increasing. In particular, more than 30% is reused of the effluent is reused in California. Here we have a distribution of recycled water in different categories. For example, here we have that 26% of recycled water is reused in agriculture, 28% landscape for golf course irrigation, 15% industrial commercial application, and 24% for potable use. And here we have a distribution of recycled water in different areas of California. So in the south of California, most of the recycled water is reused for potable use. In the center of California, in particular in the center of San Joaquin Valley, most of the recycled water is used for agricultural irrigation and so on. So reclaimed water is a blend of domestic water, in some cases industrial wastewater, and stormwater runoff in some cases. But what I want to point out is that reuse of reclaimed water is site-specific. So it depends on the source of primary wastewater, on the water treatment plants and its management, and policies and regulation. So all the benefits and risks that are related with the use of wastewater depends on different parameters and depends on the reclaimed water quality. For example, we can consider nutrients load, salinity, phytotoxic ions, suspended solid, pathogens, and so on. Depends on the amount of water used for irrigation, depends on the crop tolerance to salinity, phytotoxic ions, and in particular in terms of cultivar and rootstocks, depends on leaching fraction, depends on the soil, in particular on the drainage and texture, and depends on the irrigation method. So, feasibility study was needed and committed by Napa Sanitation District in California. So the idea was, in this study, was to test if wastewater could be used in a long-term extent in vineyards. And in particular, the most of the results that I will show you have been published in this paper that is available for download on this link. So this study started considering and analyzing recycled water in the Napa Sanitation District. So we analyzed this water by using a 24 hours automatic sample. And we also analyze other water sources, in particular wells and surface sources, but also domestic source. So what we analyze, the parameters analyzed are related with salinity and sodicity, are related with the concentration of sodium and chloride, but also the concentration of boron and other important values and parameters such as magnesium, potassium, nitrogen, and phosphorus. So, in order to understand if the reuse of recycled water can improve soil salinity, so we started to relate some parameters such as electrical water conductivity and electrical conductivity in the soil, and we considered leaching. So in order to estimate if there is an accumulation of salts, so we can estimate this considering a model. So we consider the value, the amount of the level of salinity in the water, the leaching fraction, and the irrigation method. So in our case, according with the results of our analysis, the soil electrical conductivity of water was 0.95 decisiemens per meter. So we consider as a leaching fraction, considered as the percentage of infiltrated water that drains below the root zone, we consider a value of 10%. And then we used this graph that divided the crops in 4 categories: sensitive crop, moderately sensitive, moderately tolerant, tolerant crop. So this graph allows us to relate electrical conductivity in the water and then estimate the electrical conductivity in the soil. So considering our value that is 0.95 and considering a leaching fraction of 10%, so the estimated value of salinity in the soil was 1.28. So with this simple equation, so we just realized that in soil electrical conductivity over the long term will not exceed 1.5 decisiemens per meter. That is, for vineyards, is a good value. This evaluation was important because soil electrical conductivity can be involved in decreasing the level of yield in vineyards. In fact, this can be described by an equation developed by Maas and Hoffman, and this is a simple equation where we have 2 constants, A and B. The first one is salinity threshold, and the second one is the slope. We, considering the model, the previous model that gave us a value of 1.5, if we put this value here, we do not obtain a decreasing of yield. But this was not enough for us because we just analyzed the soil. In particular, we analyzed the soil after 8 years, irrigated after 8 years with recycled water, and the value of electrical conductivity was low. So the electrical conductivity were less than 0.5, so far below the yield threshold of 1.5. But it's not always like that. I will go just for a few minutes out of the feasibility study in Napa sanitation district. I will show just some results about another study performed here in the middle of California, in Monterey area. So researchers analyzed the quality of water in different sites. They analyze sodium absorption ratio, sodium chloride, and electrical conductivity. And after many years, if you can see here, the black line is the control, and the other lines are represented by these sites. So what they observe was an increase of chloride and soil electrical conductivity, and also something related with sodium and sodium absorption ratio. So as I told you before, the reuse is site-specific, depends on many parameters. Probably in this area, the leaching fraction was not enough to drain the salts in the deepest part of the soil. Probably also the growers used amendments with chlorine inside. So that's why they obtained this type of results. So for sure there are mitigation options, like eliminate the amendments with chloride, increase the leaching fraction, improve the drainage, and used tolerant crops and varieties. So, but coming back to the Napa sanitation district study, we also evaluated the possible toxicity of chloride. So it depends on the ability of the plants to translocate or restrict the chloride in some part of the plants, so from roots to shoots, petiole, and leaves. But here there is a chloride tolerance limits for cultivar and rootstocks. Here there is a list of tolerance in terms of soil chloride concentration or chloride and in the irrigation water. So it depends on varieties and rootstock. In our case, the chloride was 4.3 milliequivalent per liter, so was not toxic for vineyards. But we also consider sodium and sodium absorption ratio. So we also here there are direct and indirect effects. In particular, sodium can be toxic for the plants. Also here there is a variability in terms of cultivar and rootstocks, but can also create some nutritional imbalances. Can also have an indirect effect on vineyards, disrupting the soil physical conditions, but there are the mitigation action are, for example, improve the level of calcium inside the soil, so then we can decrease the negative effect of sodium in the soil. But it is also important to point out that there is a relationship between electrical conductivity and sodium absorption ratio. So this relationship can allow us to divide, this graph in three categories. With, in this area, if the values fall in this area, we can have a severe reduction in infiltration, or in this area, no reduction in infiltration. Here, slightly to moderate reduction in infiltration. In our case, the SAR was 3.9. So no problem in terms of negative effects on soil and crops. We analyzed also boron. Grapes are very sensitive to boron. So also here there is it depends on the ability of routes to translocate the boron on the leaves. Here, for example, there are some toxicity effects on leaves. In particular, we have some symptoms in the leaf margins. Or here we have the typical leaf cupping. And the threshold that shows the grapes is between 0.5 and 1 milligram. So under these thresholds, that it depends on rootstock on varieties, we cannot have negative effects on plants. But in our case, in the water that we analyzed, the value was 0.4, so no problem in terms of boron in the water. So we analyzed also trace elements. In particular, we analyzed different parameters like heavy metal and so on. So, but all of them were under the recommended maximum level. So these values were well below the established thresholds. And I conclude this feasibility, the results on feasibility studies, considering the nutrients. This is an important part because we just analyze the water and we obtain these values. So in the recycled water, we add like 13 milligrams per liter total nitrogen, 0.9 milligrams of phosphorus, and 18.8 milligrams per liter of potassium. So these values are important because these nutrients can be reused and can be considered in the fertigation plan. For example, in Napa Valley, in case we have an excess of nitrogen in the water or in the vineyards, are used cover crop with cereals or other grasses that can compete with the vines for nitrogen. For sure, we have to manage these values because a high level of nitrogen can create problems in excess vigor of the plants, and in particular phosphorus, potassium were under the levels that, so no problems for vineyards in this case. So, in order to improve the reuse, the sustainable reuse, and give value to these nutrients, we can use different technologies, in particular to reuse wastewater. In particular, Napa Sanitation Districts publish a report of chloride monitoring, so the growers can go in the portal and check the value of chloride, and also publish the other parameters, in particular nitrates, the concentration of potassium, sodium, and so on. So the growers can be informed about what type of water they are using in their vineyards. But what we developed in Italy was a system, a new technology made of hardware and software systems that allow us to reuse in a sustainable way wastewater. So this is not a project, is not a prototype, this is a reality. This system is located in Italy, in the southern part of my region, Puglia, in Gallipoli. In particular, what we did, we installed sensors at the end of tertiary wastewater treatment plant. So we installed sensors in the water before to be distributed to the growers. And in particular, we installed a sensor, ion selective sensor that was used to analyze ammonium, nitrate, potassium, and chloride. We also analyzed orthophosphates. We analyzed electrical conductivity, and all these sensors were connected with this control unit that allow us to manage the signal and then develop a software. This is what we developed. This software then is divided in two parts. The first part, is to check the quality of water in real time, and the second part of the software was concentrated on, was focused on the automation of irrigation. So here is an example of some tools that we have developed. Here we can see the monitoring of ammonium and nitrates along the irrigation season. And here, growers can log in inside this portal. They can put information about farming, some characteristics of the farms. For example, the surface area, some information about the crops that is irrigated with reclaimed water, some soil characteristics, and some characteristic of the agronomic practices used and precipitation in a specific range of period. And then at the end, the output of this software is to elaborate a fertigation plan for each phenological phases, and to calculate the amount of nutrients used present inside the recycled water, then eventually also to consider some fertigation, and then at the end to calculate the new smart fertigation plan that take into account the nutrients that are inside the wastewater. So here we have another tool that allow us to have allow the growers to have a list of fertilizers used during the irrigation season, and then here some automation, so they can remotely use the valve open. They can open and they can switch on or switch off the valves. They can control them by the program runtime, or control them by using soil moisture sensors. So then, at the end, just another tool that we have developed is, is possible to monitor temperature, soil moisture, and also soil electrical conductivity. So then we can monitor electrical conductivity in the water, electrical conductivity in the soil, and then everything is under control. So just a couple of slides more, and I conclude. I will show you some information that I collected in this document, Superintendencia de Servicios Sanitarios de Chile. So in Chile, there are 531 wastewater treatment plants that produce 1.26 million of cubic meter of treated wastewater, but only 0.8% of reclaimed water is directly used in agriculture. So here we have a distribution of treatment plants along the country. Most of them are concentrated in the middle area and in the central area, sorry. And here there are all the technology used to treat wastewater. But the most important thing is the concentration in recycled water of nitrogen and phosphorus is interesting. So there is a huge potential of reuse in agriculture in Chile. And here I made like a kind of scenario. So here there are, the regions, the wine regions, and here this city is Curicó, and I identify a treatment plant that is here, very near to the vineyards, so can be easily used reclaimed water for irrigation. And just to give you some numbers. So if we applied, this is just an example, maybe different, if we applied like 50 or 90 millimeters of water as a irrigation, and content in reclaimed water of nitrogen, phosphorus, and potassium is at this level, and this is the annual fertilizer requirement, we can save in our fertigation plant almost 40% of nitrogen, 10% of phosphorus, and 30% of potassium. So this can be a good advantage for growers that can save money for chemical fertilization. So just my few conclusions. Recycled water is suitable for irrigation of vineyards over the long term in Napa vineyards. Reuse is site-specific. Then when reclaimed water is needed, is also needed a feasibility study in order to evaluate all the elements, all the specific anions that we evaluated in California. New technologies can help us to reuse in a sustainable way reclaimed water, and in Chile, reclaimed wastewater has a huge potential for be reused for irrigation purposes. So thank you so much for your attention.